Okay, for this segment we're going to be talking about Newton and planetary motions. So far we've talked about Kepler and empirical laws and how we've got the motions of the planets predicted, but we don't know why. And Newton comes along and explains it in terms of physics and how it really works. And so the first thing we're going to do is talk about the need for the centripetal force and gravity. So I just want to recap on Newton's laws of motion. I'm sure you all know these already. So the first law is also sometimes called the principle of inertia, which is that every body continues in a state of rest or in a state of uniform motion in a straight line unless it is compelled to change that state by a force acting on it. The second law is simply F equals ma, which we'll come back to. And the third law is, for every action, there is an equal and opposite reaction. There's also a fourth law, which isn't usually considered under the main ones, which is Newton's laws of universal gravitation, which basically says two bodies attract each other with a force that is directly proportional to the mass of each body and inversely proportional to the square of the distance between them. Although I think most of you are probably more comfortable with the equation, which is F equals g m1 m2 of r squared, where g is the gravitational constant, m1 is the mass of one of the bodies, m2 is the mass of the other body, and r squared is r is the distance between the two bodies. Okay, so where does centripetal force come into it? Well, if we have a body, for instance, we have the sun here and the earth here, if there wasn't a force acting on the earth, it would keep going in a straight line. The fact that it goes around in a circle tells you that a force must be acting on it. That's Newton's first law. And the force that's acting on it is gravity. The mutual gravitational pull between the earth and the sun is what gives rise to the centripetal force that holds it in place. It's the same as the string that would hold a ball in place if you were swinging it around in a ring on the end of a string. And so for a planet, the circular motion is just down to gravity. And you all know that F equals mv squared upon r is the force due to the centripetal force, but we will now derive that. And in order to do that, we'll need to go through a few steps. But if we've got a circle, then we know that the period p, that is the time it takes for the Earth to go all the way around its orbit, is given by the circumference, which is 2 pi r, and the speed at which it's going. So the speed it's going at is 2 pi r over the period p. And so we've got a measure of the force in terms of the radius of the orbit r and the period of the orbit p. And this is what's important when we want to compare to Kepler's laws. But before we can go there, let's revisit the idea of centripetal force and what's going on. So here I've got an orbiting planet. I've got a planet at position A and it moves to position B. It has a constant, I'm going to assume it's circular motion, so it has a constant speed, but its velocity changes because its direction changes, so from V to V prime. But it's always at a distance r from the center of the orbit. And so here you can see a nice vector diagram of how the velocity is changing. We're going to go through this in some steps. So I've got a circular orbit, radius r, constant speed v, and velocity changing. At at position A, the time is t, and at position B, time is t prime, and so t minus t prime is delta t, that is the time it takes to go from A to B, and that is very small, it's an infinitesimal. And that actually gives rise to this change in velocity. So we have velocity here, and it moves to this direction, so we've gone from this velocity to this velocity, so our change in velocity is delta v, and that's given by this change in direction. If the angle is small, remember that this is that change in direction of motion for the velocity, and this is the change in direction of the radius vector, so we've got this delta theta. If that is a very small angle, and we're working in radians, then the delta theta is given by the distance traveled s over r. Okay? The speed is constant. Circular orbit, the speed is constant, and so the time it takes to go from A to B is delta t. We already defined that down here. And the speed it's going at is v, and so that distance is v delta t. And so we can plug this in, and we get that the change in the direction of the velocity, delta theta, is given by the speed, the time, and the radius. But we also have this here, that the delta v upon v in this triangle will also give us theta, and so we can equate those two. So now we've got v delta t upon r is equal to delta v upon v. And that's where we've got to. Now, that means that we can rearrange this to have the acceleration, which is just delta v upon delta t, is v squared upon r. So that's the centripetal acceleration, but F equals ma, and so we have F equals mv squared upon r, and that's where that comes from. So now again we've got the period, and so we can plug in the v squared as being 2 pi r over p all squared into this equation. So now we've got the force back again. But we've already said that that centripetal force is given to us by gravity, and so that means that the force that is holding the planet in orbit is just gmm upon r squared, where in the case of the Earth around the Sun, big M would be the Sun, little m would be the planet. Likewise here, little m is the planet. Okay? And we can rearrange this, so I've just done this equal to this down here. And I can do some rearranging, so I can move my r squared up here to get an r cubed, I can cancel these little m's, and I can move my 4 pi down here, and my p squared up here. And I will get r cubed equals a constant times p squared. So here's the gravitational constant. This is the mass of the central thing. In the case that we're talking about here, this would be the Sun, and here's just 4 pi, so that's all a constant. And so r cubed is proportional to p squared. So we've essentially proven that the Kepler's third law is a result of gravity holding planets in orbit. And in fact, we can go further than that. We can see that we talked about this in class, that we have r squared equals k p cubed, r cubed equals k p squared, where this k gives you the mass. So this means that for the planets, I've got the distance of a planet from the Sun, and I've got how long it takes to go around. Those are things I can observe, and therefore I can work out the mass of the Sun. Likewise, I can work out the mass of Jupiter. I can watch the moons, see how far away they are from Jupiter, and there are 62 of them, so I can check and make sure I get the same answer each time. I can look at how far away they are, and I can look at how long it takes them to go around, and that will give me the mass of Jupiter. And this is, in fact, how we determine the masses of stars. And in fact, you'll see that this is how we determine the masses of stars in general. But in that case, we usually have binary stars. It's only fairly recently that we've discovered planets around other stars, which I'll come back to later. And so you actually have to have a system where you have two masses where neither one is dominant. Whereas for the Sun is so massive that when you do F equals ma, the force of the Earth on the Sun is so small that its acceleration is tiny. And so it just isn't doing much. It isn't moving much. It's essentially stationary. It's not quite. Whereas if you've got two masses that are similar, then like, for instance, Pluto and its moon Charon, then you've got similar masses, and so the center of mass is not inside either of the bodies. And if you go through a similar derivation, you get this, where instead of just having the big M, you have the sum of the masses. But you can still use this to derive the masses of the individual pieces. And this will in fact be one of your homework questions. And that's the end of this section.